Alright, welcome. I'm going to walk us through the Space Shuttle regression problem, and we'll see how that works using our calculator technology. And so let me switch off from my happy ugly mug to something that we can use a little bit. Space Shuttle Challenger tragedy, and we're going to do this from a statistical perspective. So basically, we've got some issues with launch temperature and the number of O-rings that are available on the shuttle. There are 16 O-rings total, and they are in pairs, and failure of two pairs of O-rings at a common joint in the shuttle would result in a tragedy. So the tasks are to, first of all, we're going to find a best fit linear function. Then we're going to find a best fit quadratic function. For both of those, we're going to get our correlation coefficients. And based on the correlation coefficient, we're going to decide which of those two processes gives the best fit for the data. And then using each of the equations, the linear and the quadratic, we will predict the number of O-rings that would be expected to have failed. Now, we know in retrospect that the Challenger did explode, so we're looking back on history with a luxury that those that made the decision didn't have as they looked forward. So the first step in the process is we're going to input our data, which will be our launch temperature in degrees Celsius and the corresponding number of O-rings that failed in all of the shuttle launches prior to the Challenger. And as you see, we have our data in place, and I've gone ahead and input that into the calculator just out of convenience. So we've got our list 1 includes or contains the temperature data, and list 2 the corresponding number of O-rings that failed for that particular launch. Our data in place in the calculator using list 1 for our temperatures and list 2 for the number of O-rings that failed on all of the prior launches. We're ready to run our calculator steps to do the linear regression. So once we've got the data input, it's convenient to look at a graph of the data. So I've got a scatter plot set up, and when we examine that scatter plot, it's pretty clear that the points are not going to be very linear. So we're not expecting great results from a linear regression process because the data is kind of scattered around and a single line is not going to match up exceptionally well. But having looked at the scatter plot, we're going to continue to run our linear regression process. So we've got our command set up here, and our X list is the temperature, our Y list, the number of O-rings that failed. And it's critical to note that I'm storing the equation in Y1. If we're going to make predictions, you've got to store the equation in your calculator, so the calculator will have that for the prediction process. And so make sure you store this equation. We're going to put this one in Y1, and since later on we're going to do a quadratic regression, we'll store that quadratic regression in Y2, and we'll have them both to use for our predicting process. So we now do our calculation, and we've got our linear regression equation here, and in the form y equal ax plus b, with the a value negative about 0.11 and b is about 2.72. And the r squared we're going to use for comparison. R squared is 0.29 rounded off to about 293, and we're going to treat that as a percentage and call that 29.3%. And that simply suggests that this linear regression equation approximately fits the data about 29%. So not a great fit, but in the field of statistics, that's better than a lot of circumstances one might encounter. Okay, for our predicting process, we want to predict the number of O-rings expected to fail at a temperature of 0 degrees Celsius. So using our regression equation, in this case it's a linear equation, first thing we're going to do is we're going to set up our table that's above the window button. So second window will bring you to this table. We're going to start that table at a value of 0 and have the other settings as you see them. Then to look at the table, table is above graph on your calculator screen. So second graph, we can see for an x of 0, we have a y1, that was our linear regression equation in y1, gives us a value of about 2.72. Now the y values that we see are O-rings, and so we're going to round this to the nearest whole number, and that would round up to 3 O-rings would be expected or predicted to fail if a launch temperature were 0 degrees based on the data. So we draw the conclusion, if we use linear regression, we predicted that 3 O-rings out of the 16 on the shuttle would fail at a launch temperature of 0 degrees Celsius. Prior launches, there had been prior launches where 3 O-rings failed and then nothing happened. So the decision was made to launch. Now we're ready to run our calculator process using quadratic regression, and just recall we've got our data input. The X list is list 1, that's our temperature at launch time. The Y data is list 2, those are the O-rings that failed on all the prior launches to Challenger. So we'll look at a scatter plot, and just a reminder that the data wasn't very linear, but it's possible that we could believe that having curvature to the data using quadratic might give us a better result, because the data seems to have some curvature. So we're going to, for that reason, we run the quadratic regression. The command to do that, instead of selecting linear regression, when we go to our statistical calculation menu, we choose quadratic regression, and everything pretty much is the same. Our X and Y lists, list 1 and 2, and in this case we store our regression equation in Y2, so that we'll actually have both equations, the linear in Y1 and the quadratic in Y2. And so the result of that quadratic regression process gives us an equation in the form of a quadratic, ax squared plus bx plus c, with the appropriate values for a, b, and c. And of course, all of this information has been stored in our calculator screen for Y2, where we can use that equation result to do predicting. But note that our r squared value in this case is about 0.48. For the linear, it was about 0.29. So with r squared equal 0.483, we're working at about 48% accuracy. And that's a substantial improvement over the linear. So based on a predicting using quadratic regression, we expect a more accurate result. So having run our quadratic regression process, we're ready to look at our prediction of number of O-rings that we would expect to fail at a temperature of 0 degrees Celsius. So this will actually show the predictions we made using both of the regression equations. So as before, our table is set up to start at a 0 value for corresponding to the 0 degrees. We look at the results in the table, and in the table our Y1 value is based on the linear regression, and our Y2 value is based on the quadratic regression. So you notice that there is a difference in those values, and again, if you haven't stored the equations in your calculator, these columns will be empty. And so our conclusion that we draw based on the linear regression is that we predict that 3 of the O-rings would fail. We rounded off from the 2.72, and that's 3 out of 16. And as before, we'd seen they had a launch where 3 O-rings failed and the shuttle made it through the process. But for our quadratic regression, we have a prediction that 10 of the 16 O-rings would fail based on the launch temperature of 0 degrees. And based on the design, this prediction will assure that the shuttle will be destroyed. There's no doubt about it. And again, we look back and we know exactly what happened, and we have the luxury of looking back. So let's don't be too hard on the people who had to look forward. But I hope that helps you with the process of doing predicting using both linear regression and quadratic regression in a problem that I think is kind of interesting. So till next time, I'll see you later.